Ladies and gentlemen, our next presenter is Dr. Lloyd Eldred. Lloyd received his PhD from Virginia Tech's Aerospace and Ocean Engineering Department. He is the creator of the parametric automated finite element modeling generation program LOFT, which you'll learn about more today, but it's also available for public use. And last but not least, he has worked for NASA for nearly 30 years, focusing on multidisciplinary system analysis for aerospace vehicles and supporting numerous projects across multiple NASA centers, including serving as the sub-project manager for NASA's Advanced Composites project. Today, Dr. Eldred will be showing us the impressive capabilities inherent in the Spark workflow, providing a powerful yet easy-to-use process for vehicle design space exploration, pairing parametric model and loads generation with the sizing fidelity of HyperX. Dr. Lloyd Eldred.
All right, thanks everyone for sticking around to the last couple hours. I think you're actually waiting for Dr. Sy. So he's up next. So my co-author, Alex, has been here. He just went to the front gate with two of our foreign nationals who are departing, and he'll be back shortly. And also sitting in the back is Chris Hullman, who's done a lot of the work that I'll be referencing and has been testing our tools. So my presentation, I'm going to talk a little bit about motivation. I'll give you an overview of our new tool, Spark, and then I'll spend a fair amount of time talking about HyperX integration, talk about some results and draw some conclusions. So the branch I work for, the vehicle analysis branch here at Langley, is a conceptual shop. We get handed very early ideas that we want to explore broad design spaces to try to narrow down what can work and whether it'll work at all. And that can be aircraft, it can be landers, it can be rockets, it can be anything that goes fast generally. And we want to be able to provide informed structural design input at the earliest possible stage of this conceptual development. Historically, on most of these vehicles, the structures guys have sat there and twiddled our thumbs while the aero guys or propulsion guys and the trajectory guys are sitting there iterating and refining their design and producing a new design every day because we couldn't catch up. You know, their configuration would change 3 times in a week, and we'd still be trying to model something that they built, you know, that was their baseline 3 weeks ago. So we've decided that we wanted to no longer do that and be able to participate in the earliest parts of the design studies when we don't have input from any of those secondary from our point of view as structures people, discipline. So we may only have very broad system parameters, you know, a weight, a speed regime, a performance criteria. It has to be able to do a 3G pull-up, that kind of very broad requirement as our inputs. We have an existing legacy toolkit that we use for meshing, solving, and sizing that we don't want to get away from. We want to continue to use it. And we want to enable rapid exploration of the design spaces for both components and full vehicles. And we want to be able to mature and refine the design as the system matures. So as we start to get the aero converging and the trajectory converging, we want to be able to pull those details into the model and support them and improve the design. So Spark is a backronym. We had another tool that was called IDEA. So Spark is the low maturity version of IDEA. And then I rationalized that it meant Structural Preliminary Analysis for Aerospace Vehicles. It has a user interface that's a text file in a JSON format. We have system coding in Python. Our structural and load modeling is in a tool called LOFT that I wrote, and I presented on 2 years ago here. I'll talk more about it in a moment. Our load case creation is in Spark, and scaling using an in-house tool called ParseNAS, which just reads Nastran input and output files and generates reports on the load resultants. We do our structural stress solution in Nastran, and then we do weight estimation and structural sizing in HyperX. This tool is currently in active use for component design studies, such as 50 different wing designs for a high-speed vehicle. Chris has been doing that for us. So why are we using Python? I hope that's obvious to most people here. It's a common, free, modern coding language. It has a huge variety of tool libraries available for free. It has a JSON to Python dictionary that's built in. It has a HyperX, that's where the HyperX API is defined and documented, and it can easily drive standalone tools by writing and reading text files. So Loft's input and output files are text. Nastran's input and output files are text, and ParseNAS reads BDF and FO6 files and writes text and comma-separated value CSV files that can be read in Excel or in any text editor. So, tiny bit about Loft. Loft is a general purpose, parametric, conceptual level aerospace structural model creation tool. It is free to download and use. It is available on software.nasa.gov. I gave a paper on it at the SciTech just over a year ago. The manual is available on NASA's technical report server. And we have a NASA Teams group. If you're a NASA employee, you can join that Teams group and you get the latest and greatest version of the code. You get the tutorials, you get discussion. This QR code will take you to a Linktree page about it. I also have this on the conclusion slide, and it's also on the piece of paper in the back on the table with some 3D prints of some of my models. So, or come up and ask me, and I'll tap my digital business card, and you'll get the same information. So, why are we using Loft and Spark? Loft, we've created parametric templates for the models that we're using in Spark, and Spark is able to modify the defined parameters. So if we have a wing model and we've defined the span and the chord, Spark can change those based on user input. All Loft outputs, Loft is used to output commented Nastran mesh with hypermesh style comments so that those models go into HyperX cleanly. Loft is also used to create partial and surrogate models that are used for the analysis in Spark. For instance, we can create OML models of an orbiter or tank-only meshes for load mapping. We can rotate our tank meshes to align with the acceleration vector for easier hydrostatic loading. We can map wing meshes of complex multi-crank wings to a 0-to-1 square mesh in order to make it easy for Spark to compute percent span and percent chord for load mapping. So, skipping ahead, Spark uses HyperX to inform our design decisions and to explore the design space. And then we directly refine the final Spark created configuration. The updated API that's in HyperX, we're accessing via an in-house Python code called HXLoad. We previously had a Visual Basic code called HSLoad that drove Hypersizer. So we're familiar with the logic of running those kinds of things. The bucket links are automatically calculated by HyperX based on the Loft property assignments. And we're planning to add support for HyperFEA iteration and analysis documentation with the HyperX dashboard. So how are we interfacing with HyperX? Loft creates the comments in the Nastran file that enable the group creation in HyperX. It understands what parts of the mesh are the upper skin of the wing or the dome of a tank, and it labels things appropriately, gives it an English name that means something, so that when you get a result out of HyperX at the end of things that has a negative margin, you go, well, the wing upper skin has a negative margin, rather than component 4006 has a negative margin. It's a lot more meaningful. Then HyperX analyzes the structure and can be opened to view the results mapped onto the mesh. So here's our input file that labels a component as strake rib, and that flows through into HyperX, and you can see it in the report as the same name and the same property ID. HyperX, we're driving with a lot of templates. We're using predefined a user template to set the material, the panel design, the load cases, the failure criteria, all of those settings in HyperX. We can either have something as simple as a simple metal plate for a quick design space exploration where we just want to get relative weights of some ideas, or we can have a complex composite layup template for a more mature design, and we can tune the analysis effort with the design maturity. My example here is actually a wing from early low boom flight demonstrator work, complex curvature wing. So, the status of the tool. The system design and initial documentation are complete. The HyperX API tool has been written and is working with analysis definition, mass reporting, and margin checks. It will report back to us on all of those things. We are currently working on the structural analysis module, so we have a wing module that's complete. We have a tank module that's complete. We can do partial vehicle analysis of any working component. So if we have a full vehicle that has wings and tanks, we can apply loads and size them in situ on the full model of the vehicle. We don't have to have a separate model that's just the wing. The fuselage module is in development. We've defined that. We have our example cases and we're working on the coding. And once that is complete, we will have the capability to do full vehicle analysis of just at least those vehicles that you can describe as a wing, a tank, and a fuselage. Just an awful lot of aerospace parts. So one of the other things that Spark does that sets it apart from just a glue program is that it allows you to create generate load cases for your analysis. And these are typical, at this stage, typical driving cases for a vehicle. So for a wing, it is the max maneuver load. And all we need in order to calculate that load is the vehicle mass and the mass maneuver acceleration. And that tells us how much lift the wing needs to support. If you're doing a 3G pull-up, you need 3 times the mass in terms of lift. For a vertical tail, we're doing an engine out case as the design load. For a tank, we're doing a max hydrostatic load. For a fuselage, we're doing a runway bump. We can and will add more design loads down the road, but these are the first cut. They're demonstrations, and they'll get us in the right ballpark with a single load case on an awful lot of vehicles. Loft is used to generate lists of nodes and elements to apply the loads to. For instance, it'll give us a list of the upper and lower skin elements on a wing. Even if you have ribs and spars and carry-throughs and all kinds of other things, it knows what elements are which. It can give us all elements above or below a specified Z coordinate if you want to do hydrostatic loading, where we've applied initial rotation to align with the acceleration vector. We guess where the free surface is, and everything below that, it's just rho GH. And then because it's aligned with the acceleration vector, it's a single coordinate. There's no dot products, nothing needs to be done in order to calculate that hydrostatic loading. And then Spark creates the Nastran load and case control cards for each of these load sets. So a little more detail about each of the modules. Here's the wing module. The user selects from the available load set types. In this case, it's just max acceleration, but we're also using the wing code for the tail surface, obviously, and that's a engine out case. So it's a different case, but all we need to know is how much lift the wing surface needs to be able to support. Loft generates the files for the upper and lower skin elements and the root spar nodes, so we can apply boundary conditions. And then the wing module either applies constant pressure to the upper and lower skin surfaces, or we can do an elliptical span-wise and triangular chord-wise load case, then performs load scaling and an internal load calculation to produce the internal loads that HyperX needs. Spark can be used to directly modify the geometric parameters for the wing, so we can change the size, the shape, the number of ribs, number of spars, the sweep, the taper, anything we want to do a design study of. Spark has access to and can modify the loft input file to make the model do that. We do intend to support, in the short term, Nastran aerodynamic calculations. Since we already have a Nastran model, we might as well do vortex lattice or some of the other panel methods that are built into Nastran. And then we'll also support mapped aero from CP Aero or Fun3D or some other tools that we use in-house, but that's a little bit further down the road. So here's some results from the wing module. Here we're just varying the gross weight of the vehicle and reporting results from HyperX for the weight of the lower skin, the upper skin, the spars, and the ribs. Performs pretty much as we expect. Nothing really exciting there, but it's working. We can vary the inputs and get a different output that makes sense, and we can get some engineering insight into what's going on. So the tank module, we can use basically arbitrary shaped tanks. Here's a pill-shaped tank. Loft will generate both the tank model as intended and a surrogate tank model that's rotated to align with the acceleration vector. The tank module can apply ullage and or hydrostatic load cases, then run Nastran once, find the reaction load, compare that to the predicted load based on the volume of the fuel, and then perform a scaling factor so that we get the right amount of load regardless of how accurate our free surface prediction was. And then calls Nastran a second time to actually do the internal load calculation that we're going to use for HyperX. Boundary conditions currently are chosen at the max location along the axes. Spark can then iterate on the free surface location if we want, or just adjust the load scale. And again, it can directly modify the loft geometric parameters to change the radius or the length or the dome curvature, those kinds of things, if we want to be able to do a design setting. And here are some examples showing the loads from a 45-degree angle acceleration and the calculated margin of safety out of HyperX when we've sized it. And then here are some results for a spherical tank with fill percentages going between 1% and 100%. And in this case, we chose to do the slightly unrealistic approach of allowing the top and the bottom hemisphere of the tank to be sized differently. We would not do that on a real vehicle, but this allowed us to understand what HyperX was doing a little bit better and understand that we were getting different results as we'd expect in this rigged case. So here's a little bit more of our partial vehicle loading. We can Spark is smart enough to know what parts of the vehicle are wings and what parts are tanks, and it's happy to size things in situ on a full model. So here's our two-stage orbit orbiter. You can see a 3D printed version of that model up in the back, and we can look at the mapped wing pressures on the main wings and the tail, and the mapped internal tank pressures on the LOX and hydrogen tanks within the vehicle. In work, we are working on a standalone fuselage sizing capability where we're taking the fuselage of that same vehicle and we're pulling the tanks and pulling the wings so that we're sizing just the fuselage component. And to do that, we're putting in point masses representing the payload and the fuel and the tanks. And then we will apply a 2G runway bump as our initial sizing load case. And Loft is creating all of these spiders in the point masses in order to apply all of these loads. If we're working with half vehicles, it can create symmetric boundary conditions along the center line or full models. We can grab the landing gear attachment points for boundary condition applications. So this all automatically happens. And then when we go back to the full vehicle and want to size the full vehicle, we can use all of the loads that we've done for the wing and for the fuselage, but we will pull these point masses and replace, put the tanks and the fuel back into the model. So Conclusion, Spark is a preliminary structural sizing environment that connects to high-fidelity tools, including Loft, Nastran, ParseNAS, and HyperX. We use at the moment, a single critical design load case for each component, and then scale them to the desired magnitudes. And HyperX's API allows it to either be treated as an analysis black box, where Spark is doing all the work, and using HyperX just to give us a number we need for our design studies, or HyperX can use Spark as a preprocessor to set up a problem that you then go into HyperX and do all your work with your tool, with all of its powerful tools to refine your design and add more detail to it. Or you can do both, which is really what we're intending to do. So that's... I see someone stretching in the back. Yeah, sure. So I tried to point out Alex earlier, he was off dealing with foreign nationals. So he's done the bulk of the programming of Spark. I've done most of, or all of Loft, I guess, and little bits of Spark. So go ahead.
Yeah, so you might have mentioned it before, but is the goal of this tool just to evaluate specific points in the design space, or do you do a more exhaustive exploration where you look at trends to see if I change the sweep, what will that do to the weight? Identify the key drivers. What's the goal of this tool?
Right. The intent is to enable us to do more of a design space exploration with all kinds of different multiple inputs. Spark supports that, and because of the use of the JSON file format, it's trivial to put an optimizer on the outside of it that would read that JSON file, change a variable, write it back out, call Spark, run it, save the output, and do that again as in a loop. I think that's 4 or 5 lines of Python to accomplish that.
Gotcha.
Yeah.
And I guess a follow-up would be, would you do it directly with the tool, or would you use the tool to build a surrogate model and then do the design space exploration on the surrogate model instead?
We're looking at those options. We're not sure exactly how we're going to store our results when we do those kinds of surveys, whether we'll just save all the data or whether we'll use it to train something else that'll give us predictions of how things perform. That's still down the road a little bit.
Yeah, and then there's some projects that are interested in using it, one of which I'm working on, and which is creating geometry and wants to use some of the features of Spark to help actually do some sizing in their multidisciplinary optimization uncertainty qualification tool that a team is working on in our branch.
Okay, thank you.
Sure.
This question's on your Loft tool. Does it make a congruent mesh, or are there some finite element mechanisms connecting the components together?
If the vehicle is a stack, like a rocket or an airplane fuselage, it all gets merged together and stitched together. If you have a fin or a wing, it does not stitch that directly, but there are newly added capabilities that allow you to easily stitch your carry through to the bulkhead that it's supposed to be glued to with rigid elements. So this vehicle that we're doing, I don't think you can see the rigid elements there at the spar points, but they're there, and they're parametric, so if we change the diameter or change the length or anything or change the mesh count, it still generates them and still connects them up properly.
Yep.
And a second question, what modules do you have foreseeable for the future? Are you going to put in ducts and inlets and some of those?
I'm not sure. We don't have a lot of those on rockets. And on the aircraft we do have ducts and inlets, but they end up getting sized slightly different way.
Yeah, I think at least for one of the project I'm doing, they have a different tool for that, but it is something that we foreseeably could put down, down the line, a simplified propulsion type module.
Yeah.
To help cover some of those type of systems.
As we get to be able to support more mature designs, this is targeted at low maturity designs at this point, and we have a high maturity tool in house that we're just trying to cover cover some space to be able to do analysis before we're ready to use the high maturity tool.
I had a question you had. So the template, when you bring it into HyperX, obviously you have some analysis properties built in. Are those adjustable or are those locked into the template?
At the moment, they're locked into
Yeah.
the template, but
Yes, at the moment, we just kept them pretty straightforward, like just locked in, but as I get more familiar with the API, I plan on investigating if I can have the user generate from that, or if I can't really get it to the amount of user accessibility, I'll just expand the templates available, and we'll probably end up being a combination of the two. Some well-used type of templates for analysis and structural concepts, and then the user can either modify those or potentially create their own. I'm not too familiar with the API on that section yet.
I guess a quick follow-up, since it's a text file to do the input parameters for it, is there any control in there for like the mesh fidelity or element quality checks? Or
both of those are in Loft. So generally, I'll put just a global mesh density variable at the beginning, that all the mesh count commands multiply something by that. So if you half it, you get globally half the mesh density. If you double it, you get globally. Or you can go in and refine it locally if you want. So that's built in. And then your other question was
element quality.
element quality. Okay, I do have an element quality check command that will report back on the screen. High aspect ratio or warped elements or those kinds of things, but they're pretty simple checks. Now, the logic that Loft uses to create meshes is not a paver. They're rectangular elements almost everywhere. So you get a clean mesh on most aerospace vehicles, but if you have something that's really distorted, or a blended wing body, it might not do it quite as well because you're inherently stretching. All right.